These are some problems on our new topic, current electricity. It's the beginning of current electricity. So these are the problems on current, resistance, and resistivity. So here's the first problem. So standard electric outlets in the US run at 120 volts. An electric kettle has coiled wire inside this kettle. It has a nichrome wire, probably, right? Dissipate power when it carries a current, warming the water in the kettle. The kettle, designed to use, carries 14 amps maximum current when connected to a 120 volt outlet. So based on this data, specification is asking what's the resistance of the wire, what power is dissipated, and so on. Okay, so these are very simple problems, actually, just straightforward if you just know the formula. So here what you have, so it says you're using output voltage at 120 volt outlet, right? So if you it says here's the coil inside, right? It says if you put 120 volt, right, it carries how much current? 14 amps of current. That's the manufacturer's specification. So based on that, you can quickly calculate the resistance of it, because from Ohm's law, V is IR, right? So R, which is the resistance of the coil or wire, is V over I. So V is 120 volt and 14 amps. So that's it. So 8.6 ohms. This is the symbol for ohms resistance. So that's the first question. The second question is what power is dissipated when the kettle is running, right? So when the kettle is running, how much power will be dissipated in the form of heat? So we are assuming all the electrical power will be dissipated as heating power. So power is, again, you can use various formulas now. Since you know resistance, you know voltage, I, right? So you just use one of these. So either I square R, or V square over R, or I times V. Since we know all these parameters, there are three formulas for power, right? One is I square R, one is V square over R, one is I times V. Since we know all of this, just use one of them. So I is 14 amps and resistance is 8.6. So power dissipated by this kettle heating coil is 1.7. So you'll get 1700 watts. Watts is the unit of power, and you can convert back to kilowatts, because if you have a big number, or just leave it in watts, that's fine. Okay, next question is it says the kettle can hold 1.7 liters of water. Assume that all power goes to heating power, right? How long will it take for the kettle to heat the water from 20 degrees Celsius to its boiling point, 100 degrees Celsius, right? So then you have to do a little bit of power definition. So the general definition of power is energy over time. It's the rate of flow of energy, right? In general, power is energy over time. Now you're heating water. So when you heat water, then remember from calorimetry principle, energy is mc of water delta T, and you are solving time. Power, we already know. Power is it's running at its full capacity, 1.7, 1700 watts, and that's it. So time, it takes mcw delta T divided by the power, right, from this equation. So mass of the water is, so convert first mass. So the volume of the water is 1.7 liter, and that's volume in meter cube is 1.7 10 to the power 1.7 meter cube. Okay, 1. Let's see, yeah, 1.7 meter cube. 1.7. I'm sorry, 10 to the power negative 3 meter cube. And density of water is 1000 kilogram per meter cube, right? So we have to do a side calculation. So the mass of water is actually volume of the water, density of water. So if you do that, so 1.7 10 to the power negative 3 liter, because 1 liter has 10 to the power negative 3 meter cube. density of water 1000, so that leaves mass of water as just 1.7 kilograms. So in short, actually, for simplicity, 1.7 liter is exactly equal to 1.7 kilogram for pure water. Okay, so 1.7 kilogram, right? We must be in kilogram, not in gram. And this C, what is this C of W? This C of W from calorimetry, right, is the specific heat capacity of water, which is 4190 from the list. Change in temperature, you don't need to convert back to Kelvin because you are calculating the change in degree Celsius. So it's 100 minus 20, final minus initial. Divided power is 1700. You must put in watts. So the time it takes is, now if you do this calculation, it's about 335 seconds, which is about 5.6. So it takes about 5 or 6 minutes to boil water, and it makes sense from practical example. Okay, so that's how you solve this problem. Here's the next problem. It says a 10 kilowatt resistor is connected across a battery whose EMF is 9 volt. The voltage across the 10 kilo resistor appears to be 8.7 volt. What must be the internal resistance of the battery? Remember, EMF means it's the constant voltage that the battery is supposed to provide. It's the maximum voltage. EMF, sorry, just to remind you, EMF is electromotive force. Is the maximum, constant voltage of the voltage supply, of the battery. It's the maximum capacity. Okay. But because of its internal, because none of the batteries are ideal, so in reality, actually, because of its internal resistance, it can't supply constant voltage. Even if it says 9 volts, when you connect a load or any external resistor, and depending on the current drawn by the load resistor, this voltage decreases actually. So that's what it says. So here's the symbol I'm going to use. So any non-ideal battery, any practical batteries are symbolized by this. Right? This is together actually. So you can put a circle. Right? This is the symbol for a practical battery. So battery has some EMF, I would say E, and its internal resistance is small r. Right? This is the symbol for non-ideal battery. Right? It has some internal hidden resistance. Right? And it says you connect this battery across a resistor or any load resistor, load, let's say R is 10 kilo ohm, right? And what happens? So if you connect this to the battery, it draws current. So we're gonna always show conventional current from positive side to negative side, right? Like this. And it says now based on this information, so what's the internal? So here the EMF, which is the maximum voltage it can generate, it can supply 9 volts, but the voltage across this 10 kilo ohm resistor we call V terminal voltage across the resistor is only 8.7 volts. So there's 0.3 volt lost in internal resistance. Based on that, it's asking what's the internal resistance of the battery. So first of all, you need the current actually. So how do you find the current? So current can be calculated by this information. It says the voltage across this external resistor, right, 10 kilo ohm, appears to be 8.7 volts. So Vt divided by R, right, from Ohm's law. 8.7 divided by resistance is 10 kilo ohms, remember, 10,000. You must convert into ohms. So that's 8.7, 10 to the power negative 4 amps, right, little current. And then after that, how do you find what's the relationship between EMF, this is called EMF, electromotive force of the battery, and terminal. So here's the relation. EMF of the battery is terminal potential difference plus you add some internal loss, I times R. This guy right here, I times small r, is internal loss. Some voltage will be lost internally. Okay, that's it. And then solve for, so E minus Vt over, right, I is equal to the small r, internal resistance, right? Small r is the internal resistance. Okay, internal resistance of the battery, that's what it is actually. So is 9 minus 8.7 divided by current is 8.7, 10 to the power negative 4, and the internal resistance of the battery is 345 ohms if you do this calculation. Here's the next problem. Again, it has to do with the heating coil. So it says an electric blanket has a wire that runs through the interior carpet, or interior blanket. A current causes energy to be dissipated in the wire, warming the blanket. A new low voltage electric blanket is rated to be 18 volt. It runs at 18 volt and it dissipates 82 watts of power. What is the resistance of the wire that runs through blanket? And it's really easy actually. It's just straightforward. So you're given its operating voltage. So it says when you apply 18 volts, it dissipates how much power? 82 power. So it's asking what's the resistance of the coil, right, used in this blanket, electric blanket. So power is one of the formula V square over R, right? And R is V square over power. That's it. So 18 volts square divided power is 82 watts. So the resistance of the coil must be 3.95 ohms. That's it. So here's some more examples. So if a 1.5 volt battery stores 5 kilojoules of energy, for how many minutes could it sustain a current of 1.2 amps? So it's basically again a very easy problem. So you're calculating how much time it takes to drain the battery completely. So we can get started with this. So again, the general definition of power is energy, right? It's energy, electrical energy divided by time, right? Rate of flow of energy is power in general, right? But power is also I times V, because why? Because you are given the voltage, you are given the current. It's draining at it's drawing current as 1.2 volt amp, right? And the battery voltage is 1. So you know current, voltage. So power is energy which is given to you. The battery has total of 5,000 joules of energy, and time, and you solve for T. So total energy of the battery which is 5,000 joules, and your power is I times V. So total energy is 5 kilojoules, right? Kilojoules must be in joules. 5,000 divided by current is 1.2 amps. Voltage is 1.5 volt. That's it. So the time it takes is about 2778 seconds, and in minutes, right? Generally, time is calculated in minutes, right? Because minute is the practical unit. It's about 46 minutes. So it takes about 46 minutes to drain the battery completely. Okay. So here's the next problem. It says that many 2 10 to the power 13 electrons flow in through a transistor. Transistor is amplification or switching device in electronics, semiconductor. You don't need to worry about you don't need to know actually how transistor works. So it's a semiconductor device, very important component. So it says that many electrons flow, right, in a transistor terminal in 1 second. What is the current through the transistor? It's really easy actually. First, so it's asking current, right? So current by definition is dq over dt, right? It's the rate of flow of charge, which is also called total charge divided by total time, right? So first you need to figure out the total charge of that many electrons, because it says that many electrons flows, right? So what would be the total charge? Is n times c, always. Total charge on any charge is total number of that. So in this case it's the electron, and times the electronic charge, right? It's the basic charge. So 2 10 to the power 13 times E is the basic charge or electrons charge, 1.6 10 to the power negative 19, right? So that's the total charge. The total charge possessed by that many electrons is, right, so you can do this calculation. It's 3.2 10 to the power negative 6 coulombs. Right, that's the total time. Just put it here, right here, and time you calculate Q over current, right? No, so what current? Yeah, this is action. I'm sorry, it's action the total current Q over time. So total charge is 3.2 10 to the power negative 6. Total time is 1 milliseconds. So you must convert into seconds. Millisecond 10 to the power negative 3, right? So that's the current. So 3.2 milliamp. If you convert that, you can just keep it in amp or just convert into milliamp. So here's the next problem. It says a 3-volt battery is connected across the ends of a nichrome wire, heating element of 1.6 millimeter diameter. Its diameter of this coil is 1.6 millimeter and 50 centimeter length, half a meter. The resistivity of the nichrome is this at this operating temperature. What is the current in the wire, right? And so on. Okay, here's the first question. So what you are given? You're given the voltage of the battery used, 3 volt, right? And you're given the diameter of the nichrome wire, 1.6 millimeter. So the radius will be 0.8 millimeter, right? Is 0.8 10 to the power negative 3 meter. And its length is total length of this nichrome wire is 50 centimeter, which is half a meter. Make sure you convert everything into standard unit during the calculation. Okay, and resistivity, remember this rho symbol, right, is the resistivity. And read my lecture slide actually about the resistivity. The resistivity is the material property. Different materials have different resistivity. It's a constant quantity for given temperature and given material. So the nichrome has that much resistivity. Its unit is ohm meter. And based on that, first of all, what is the current? So that means you have a battery, right? Dry cell battery, let's say, right? The battery, or you can just use the symbol and you connect it. This is the nichrome wire. Say you connect it to using a clipper, micro grabber, right? This is the nichrome wire, right? So this is the positive terminal, and it says what's the total current. So current will flow like this, right? Current flow in this direction. So we always take the conventional current, which flows from positive side. It says first question is what's the current, and first to find the current, right, you need the resistance. And based on this information, first you can I'm gonna use small r for the radius because big R stands for the resistance. The resistance of the given wire is this very important formula, rho L over A, because the resistance of the material depends on these factors: resistivity, length, and area of cross section. Okay, resistivity 1.5 10 to the power negative 6. Length is half a meter, and the area of cross section is a cylindrical wire, so pi r square, right? Pi radius is 0.8 and it must be in meter square. So that's the resistance of the wire. And if you do that, the resistance of the wire is 0.373 ohms. Once you have resistance, then you can find the current, right? Because current is just from Ohm's law, voltage divided by resistance. So voltage you use just 3 volt, and the resistance is 373. So if you do that, the current will be 8 amps exactly. Okay, so 8 amps current is flowing through this nichrome wire. Now next question is, what would be the current if the same nichrome wire is used but and same length but half its diameter? Now the new diameter, okay, new diameter is half the it says what would be the new current if you use the same wire, same length, but half its diameter. So half means 0.8 millimeter, right? So what's the new radius? It's 0.4 millimeter, negative 3 here. So what's the new resistance? It will definitely change the resistance. So new resistance will be rho L is same, right? But the area of cross section will be new because you change the diameter. So rho is same, which is the resistivity, 1.5 times about negative 6. Length is same, but area will be different. Pi 0.4 times about negative 3, right? So the new resistance of the nichrome wire. Now new is 1.49. It's about 1.5 ohms. So what's the new current? So new current will be, voltage is same, you still apply 3 volt across it, 1.49. Okay, so that's your new current, 2 amps. See, the current has decreased from 8 amps to 2 amps if you half the diameter of the wire. Here's the last problem for this topic. It says a 40 watts 120 volt light bulb has a tungsten filament. Usually the conventional light bulbs use actually this material, tungsten, because it can withstand very high temperature. Tungsten filament of diameter 0.04 millimeter. The filament's operating temperature is 1500 degrees Celsius, and the resistivity depends on temperature. Resistivity of this material at this temperature is this. And first question, how long is the filament? And first question is really easy, right? Because you're given, so let's write down all the given variables. So you're given the power rating. So this bulb, power is 40 watts at how many volts? So then right away you can find out the resistance of the wire, this filament, right? Resistance is voltage square by power, right? Because why? Because power is V square over R, that's why. So V square over P. So V square is, V is voltage 120 volts and 40 watts, and the resistance of the coil filament is 360 ohms, and this is at 1500 degrees Celsius when it is operating, right? So it's actually how long is the filament, right? So then we use our regular formula, rho L over A, right? And the diameter is 0.04 millimeter. The radius then 0.02 meter. Okay, so then it's asking the how long is the wire. Then you can calculate RA over rho. R is, we have calculated 360 ohms. Area is pi r square, 0.02 10 to the power negative 3. Make sure to square it, right? And divided by the resistivity at 1500 degrees Celsius is given 5.02 10 to the power negative 7. Okay, so that must be the length of this tungsten filament used in this electric bulb. And if you do that, it's 0.9 meter. It's about 90 centimeter long. Okay, that's the first part. Now second part, it says it's asking what's the resistance of this same filament, right, at 20 degrees Celsius, at much less, at room temperature basically. Now at 20 degrees Celsius, what's the resistance of the coil, this tungsten filament, right? Then you're going to need the new resistivity at 20 degrees Celsius. You have to check the table, actually the physical table in my lecture or somewhere. And the resistivity is quite different actually at room temperature. It's 5 point, is very low, 10 to the power negative 8 ohms meter. So this is from the table. Okay, you can't use this resistivity, right, the original resistivity given, because this is at operating temperature 1500 degrees Celsius, but it's acting resistance at 20 degrees Celsius, and at 20 degrees Celsius is resistivity is this for tungsten. Then it's asking what's the new resistance, right? And then just use the same. So R at 20 degrees Celsius is, R is rho at 20 degrees Celsius, right? L over A. Length is same, area of cross section is same, right? They don't change actually. So we ignore the expansion. So okay, that's it. So 5.6 10 to the power negative 8. The length we have calculated from part A, length of the wire remains same, 0.9 meter, and the area is pi r square, 0.02 10 to the power negative 3 square. The area of cross section also remains same, and if you do that, 40 ohms, right? So this is at 20 degrees. So you can clearly see at 20 degrees its resistance is only 40 ohms. So if you heat it up to 1500 degrees Celsius when it is operating and the bulb is lighting, its resistance is 360 degree, right? And it makes sense because the resistance increases actually with increase in temperature, right?